For attending our How to Properly Size and Select Your Custom Flexible Heater webinar. My name is Ryan Wood, Content Marketing Manager here at Epec. Before we get started, I just want to let you all know that you'll be muted during the presentation. If you have any questions as we move along, please enter them into the questions panel, which is located in the webinar control panel, and we'll try to get to them all at the end of the presentation. If we don't have time to go through all your questions, we'll be sure to reply to you by email. Also, we'll be recording this webinar and posting both the recording and the slides on our website and YouTube channel. Our presenter today is Stephen Goodman, our User Interface and Cable Assembly Product Manager. Stephen is a mechanical engineer with a Bachelor of Science and MBA from Northeastern. As the User Interface and Cable Assembly Product Manager here at Epec, Stephen works closely with customers to provide solutions to specific problems during design consultation and, where needed, helping with the creation of specific designs. So without further ado, I will pass it on over to Stephen.
Thank you, Ryan. Good afternoon, everyone. Again, my name is Steve Goodman, and I'm one of the product managers here today. We're going to be reviewing how to properly size and select your custom flexible heater. So our agenda. First, we'll dive in and review briefly what is a custom flexible heater. Next, we'll talk a bit about how they're designed and how they're built. Then we'll be discussing details on how to properly size and select the proper materials and design parameters for your custom heater. Then we'll be talking about further ways you can customize your flexible heater for the specific application that you're developing this for. Then we'll be talking about some steps that you'll need to consider before moving forward with a new project. And lastly, a brief Q&A session. So, first and foremost, what is a custom flexible heater? A flexible heater is a fixed resistance heating element that's then sandwiched between two layers of insulating film. Those films can be a silicone material, a polyimide material, and other types of flexible electrically insulating films. Silicone and polyimide are the two most common and typically the ones we manufacture with. Once the heater is actually built, then we need to develop a way to attach power and wires to it, and then a pressure-sensitive adhesive or another way to fix the heater to whatever surface or substrate you're mounting it to. Now, while today's presentation focuses solely on flexible heaters, Epec does support other heater technologies, including some rigid heaters that include thick film, ceramic, and PTC style. What we'll cover today will go into detail about how the length and the size of the traces within the heater provide all of the power and the characteristics for the heater, and we'll go through details on how to properly size and develop those traces for your specific application. Since Epec is a circuit board company at heart, and we make millions of circuit boards, flex circuits, and other custom electronics, these heaters are very similar to those core technologies, with the exception that the conductive material within the heater is not pure copper like the PCBs and flex. Instead, it's a higher resistant element film, and we'll go into more detail here. So again, a bit about the common materials and applications that we can support here at Epec. Within our silicone heater family, this covers a variety of applications. It ranges from aerospace to medical devices to food and beverage type applications. Our polyimide and polyester heaters also support aerospace and medical, but are typically geared for lower cost, higher volume type applications, many of which are in transportation industry and other consumer electronics. And lastly, a smaller part of our business is supporting thick film type heaters. Many of those are used in different types of lab equipment and even the element in a e-cigarette or electric kettle. So what is a flexible heater? As I said before, a flexible heater is nothing more than a resistive element sandwiched between two layers of insulating film. This slide here showcases the two primary element types that we can support. The first is a wire wound design, which is in the upper left portion of this screen here, and then an etched foil design here. A wire wound design is simply one length of wire that has a known resistance that's then wound and snaked along a flexible substrate like silicone or polyimide. An etched foil design is very similar to an etched PCB or another rigid circuit board that you're likely familiar with, except for with copper being replaced by a nickel iron copper alloy. We can also support a silk screened element type, which is very similar to a traditional polyester membrane switch, where a conductive ink is silk screened along a substrate and then laminated within 2 layers of insulating film. For the flexible heater to function, it needs power. That power is coming by 2 leads as shown here in this sketch. There's no polarity to these heaters, so they can work whether it's plus 24 volts or minus 24 volts relative to the 2 leads coming off of here. In terms of the types and complexity of heaters that we can support, there are an infinite number of shapes, sizes, and combinations of heaters that we can build here at Epec. Silicone and polyimide heaters are among our most common designs. And as shown here with these examples, there's no shortage of design considerations that can be solved by these technologies. Every one of these and each one of these is a completely custom heater design for a particular customer and what they're trying to accomplish with their design intent. So a bit more about how these heaters function. The reason copper is used on most traditional cables and circuit boards is because it's wildly conductive. There's very low resistance, and as a result, there's very little heat created. A heater, you want to create heat. So using copper as the conductive element, you won't create a lot of heat. So we use specialty alloys that are a combination of nickel, iron, and copper. And those alloys are either, as I said, in a wire wound design or the etched foil design. The way that these work is given a certain footprint, a certain wattage requirement, and a certain voltage or resistance requirement, Epec can then design the circuit trace to produce that exact amount of heat given those electrical characteristics. This is important because our customers don't need to design the circuit. They don't need to give us Gerbers. Give us the footprint, and then we can map the circuit and design the circuit, laying it out to produce the exact wattage and performance that particular application needs. It's also important to note that the length and size of these traces changes the power of the heater and how it's going to operate. The same is true depending on how hard you're driving the heater with whatever voltage. As shown here in the upper right, as you drive the heaters harder, they are prone to hot spots. Certain portions of the heater can be warmer than others. This also may be indicative of the thermal mass or whatever you're attaching the heater to. But this is important because if you try to push too much power through a heater, it can jeopardize its lifespan and its performance. So when we look at a new application, we spend a significant amount of energy working with our customers on the front end to better understand what you're trying to accomplish, to understand the input voltage and options that you have, if you have a current limiting source and whatnot. All of these are important when we size the heater. Failure to do so means the heater won't work right, or its lifespan may be jeopardized. So we're going to walk back to high school physics class and go over the 3 forms of heat transfer. The 3 forms of heat transfer are conduction, convection, and radiation. An example of conduction heat is you or I grabbing a cookie sheet out of the oven without a glove, and the hot pan burns our hand. That's an example of heat being conducted to my hand, burning me. We definitely don't want that to happen. Another example of, an example of convection is similar to standing outside with a breeze. As that air travels across your body, it's drawing heat away from your body. That is a form of convection. That can be both heating or cooling. And then the last is radiation. This is where heat literally radiates through the medium, transmitting energy, just like you standing outside on a nice warm afternoon, feeling the warmth of the sun on your face. That heat's arriving to you 93 million miles through the form of radiant energy from the sun. Of these three forms of heat transfer, these types of flexible heaters work primarily through the use of conduction. What that means is the heater needs to be physically touching whatever surface or substrate that you're trying to warm. There needs to be a direct physical contact. There may be very small amounts of radiant heat coming from the heater or air convecting off the heat, warming the surrounding area. But as I've said, the primary form of heat transfer with these designs is through conduction. Next, we'll go into a bit about how flexible heaters are designed and built. So the first step for moving into this is working with our customers to better understand what they're trying to accomplish. We need our customers to describe in some way, shape, or form the type of heater that they need. And there's a lot of ways that this can come into us. It could be something as simple as a text description, words coming in an email saying, I need a heater that's 3 inches by 5 inches, that's 20 watts, and has a 12-inch pigtail coming off of it. That very simple heater design is something we can work with and start from. Another way customers communicate these types of requirements to us is through some kind of preliminary sketch. Some people call those a napkin sketch or some kind of other preliminary document, but typically it's a very basic document with minimal information. There must be enough for us, though, to quote and have a conversation to better understand what the customer is trying to do. And the last way we get this type of information coming into Epec is through a detailed drawing. Typically, these are released, have gone through some engineering review cycle at our customer. They're revision controlled with dimensions and tolerances. Some of them, they may or may not have a bill of materials if there's a connector and other components involved. But these detailed drawings are the preferred way for us to build from. However, we can work with any of these three situations depending on where you, the customer, are at in the process of going to market. So once Epec has a drawing or some scope of work from our customer, and we quote it, and then we win it, we're then moving forward into our design phase. That first step of our design phase is where Epec creates a detailed manufacturing drawing. Every one of these drawings that we create is a fully dimensioned manufacturing drawing that includes the materials, all voltage and wattage characteristics, dimensions and tolerances, electrical connections and pinouts, and any other requirements that our customers may have. If a customer comes to us with a fully released drawing, this may be as simple as a regurgitation of the information that's already there. However, if a customer comes to us with a napkin sketch or even just a text description of the heater they want, we create this drawing and use this as a mechanism to communicate the design back to the customer to show how we interpret their design and demonstrate to them how we're going to build this. Once we have this drawing in place, we're then able to move forward and can produce these heaters in as short as 15 business days after design approval. Next, once we move forward, we begin making the heater itself. The heater themselves, we build using a variety of processes. On the right-hand side, this is an etched foil heater before the traces have been etched. This is what the heater looks like in its original unadulterated form. On the left-hand side is silicone film before it's been vulcanized, being cut to shape and processed. Since we are the manufacturer and we're building these completely from scratch, we're able to completely customize the heater with whatever you need for a design, shape, and performance. Once the heater has been built, now we need to figure out how to energize it and power it. There's a lot of ways we can go about doing this. The most common is just simply soldering some wires to the exposed pads and then strain relieving them. Some of our customers prefer not to have wire attached, and they request us to leave a small pad, potentially a through hole for a soldering tip. But there's a lot of ways we can go about attaching physical wires to the heater. Keep in mind, our heaters aren't just a heating element. We can add discrete components like thermistors, thermocouples, and other temperature sense devices. If that's part of the design, there may be more than just 2 wires needed for the heater to operate, with these 2 being for power and additional sets of wires being necessary to monitor the thermistors and other temp sense items. Once the heater is built and assembled, we go through extensive electrical and thermal testing to verify that the heater meets all program objectives. Some of the most common tests we run are 100% high pot tests, thermal cycling, and even operating the heater at different environmental conditions like hot and cold to make sure that the heater is properly working. Next, we're going to go through some tips for sizing and selecting your custom heater. So in terms of size limitations, there's a lot to discuss here. Typically, the material, the encapsulating material, the heating element are the 2 main drivers for how big, how large, or how powerful the heater can be. The lifespan of the heater can also be impacted by these variables. A small heater that's driven really hard has a high risk of burning out. So we work with our customers to better understand what you're trying to accomplish, the type of thermal mass that you're going to be using to warm, and then also the type of power and voltage that'll be driving the heater. In terms of size limitations, the smallest heater that we can make is a very, very small heater, maybe about the size of a postage stamp. If you saw the previous slide with the heater next to a penny, that's an extremely small heater. The actual footprint of these can be about 15 millimeters square. The other consideration is now that you have a heater, you need to figure out how to power it. And a lot of times the wire itself that we're attaching is either the most massive or the most thick item in the assembly, and or the strain relief that secures the wires to the heater. In this view on the upper right here, we have an epoxy strain relief that has a height of less than 3 millimeters. That's far, far greater than the overall thickness of the heater in this example, which is less than half of a millimeter. Of these designs, the epoxy design is a very small footprint, but has a couple millimeter height as shown. If overall height is a concern, we can use a silicone patch to strain relief, as shown in this image in the lower right-hand side. So now that we've talked a little bit about the smallest heaters that we can make, here's an example of an extremely large heater that we've made. This one here is well over 1 meter in overall length, but it wasn't built as one heater. it was actually built as 4 or 5 separate heaters that were all stitched and soldered together. This is important because these types of large heaters can only be built in panels and then further assembled. And within that, the silicone with wire wound heating element are the heater designs that we can make very, very large. We do have size limitations if a polyimide or etched foil heater is necessary. We cannot make them over 1 meter long. So this is important for designers and engineers. If you need a very large or massive heater that needs to go inside of a insulated tote bag like this one here for food delivery, we wouldn't be able to do one polyimide heater that's over 1 meter long. We would have to do several polyimide heaters and then wire them all either in series or parallel, or we'd make a silicone heater like this and then just wrap that around the perimeter of the cooler or whatever we're trying to warm. So next, we'll talk a little bit about how to size the element. For those who are familiar with Ohm's law relates voltage, current, and resistance, and then therefore power, because it's the same within that family. So for us to go and move forward and give you a certain wattage or performance of a heater, we need 2 of the 3 variables here in this triangle. If you're unable to provide this information, we can work with you to better understand what you're trying to accomplish and suggest an operating voltage or a power requirement that would be appropriate for your design. As I said before, these heaters are fixed resistance. That resistance is defined on the size, width, and length of either the trace or the wire that's in the heater. We commit to a plus or minus 10% tolerance band on the resistance. That's important because that directly correlates to the wattage of the heater. So for our customers who need a 100-watt heater, we can make that 100 watts plus or minus 10%. So it would be a 90 to 110 watt heater. If a customer comes and says, I need a 100-watt heater plus or minus 2 watts, that's well within the tolerance band and potentially something that's going to be difficult or impossible to make in a production setting. Real reason behind this is because although the heater is a fixed resistance heater, the data we've shown here in this slide shows that as you apply voltage to a heater and monitor the temperature versus time, the actual resistance of the heater will drift ever so slightly as the temperature raises or lowers. And in this example, this is well within the plus or minus 10% tolerance band, but still, a couple percent drift of resistance is normal. It's also important to note that the amount of thermal mass that the heater is attached to, for example, aluminum plate, an alternator, an oil filter, any type of device that you're trying to warm, the amount of thermal mass that you're trying to warm will then have a direct impact on how the heater behaves, how long it takes to heat, and what the max temperature is that it can achieve. So one of our biggest challenges in developing these heaters is working with our customers to predict how many watts we need to warm the device X number of degrees. And it's very simple to look at these curves here and estimate how much power you're going to need. But this is a rough calculation. And I know that for those who have been through either a thermodynamics class or heat transfer classes in college, there are equations to go and calculate this. In our experience, It's a lot faster and less expensive just to get a couple sample heaters, use a power supply that you can vary the input voltage, and then watch the temperature versus time to size your heater that way. I'd like to think of it as a bit of a guess and check. We use these initial temperature curves to park the heater in the right approximate wattage we need, and then actually build some heaters, test it, and then work with our customer to dial in exactly the wattage and performance you need for the heater to function as intended. And what you can see between these two charts here, on the left, there's a thermal mass involved. The heater is attached to an aluminum plate. Whereas on the right, the heater is just free, and it's really just air that it's heating. And what you'll notice is that the heater warms very fast when there's no thermal mass attached to it. When there's an aluminum plate or some other thermal mass attached to the heater, it takes time. This is no different than a big pot of water on your stove. You're trying to boil that, and it may take 5, 10, 20 minutes depending on the size of the pot and the setting that you're putting your stove on. The more thermal mass you have, the longer it takes to heat that. So once we have a heater in theory designed, and we come up with a wattage and a footprint and the voltage characteristics to operate the heater, the last step of the process is reviewing the watt density. The watt density is nothing more than the total wattage of the heater divided by the square inch area of the heater. This doesn't include other features of the heater, the strain relief. This is just the heating element footprint. As a rule of thumb, for heaters with 10 watts per square inch and below are typically no concern whatsoever. As you increase the watt density, which is driving the heater harder and harder, what you do is you develop hot spots. You potentially can see some blistering or bubbling of the polyimide because of localized non-uniform heat generation. And over time, potentially, the heater trace will burn up or fail. This is important because we have customers who come to us with extremely high power heaters in very small package sizes, and we can build it and it'll work, but we can't predict how long it's going to work for. We typically want our heaters to function for the life of the application. That's years for us. For some of these, especially the ones that are 40 watts per square inch or higher, we can build it and it'll turn on. But if it's not attached to a sufficient thermal mass, the ability to draw heat away from the heater itself, it may only last 100 hours or 10 hours. And for some of our customers who are involved in test engineering or destructive tests, they don't care. Maybe their test is only 10 or 20 minutes. So as long as it lasts longer than an hour, they're happy with their design and our solution. Other things to consider, it's not just thermal mass, it's also any forced cooling or airflow over the heater that'll change its performance. A good way to test this is to take two heaters, suspend them in air, have one just be stationary with no airflow, and take the second and put a small fan on that. If you attach a temp sense device like a thermocouple or a thermistor to the surface of the heater and watch the temperature rise over time, you'll see that the heater with the forced cooling will never achieve the same max temperature, and it'll probably take a lot longer to get there. The reason, the air is convecting heat away from the heater, allowing it to operate in a different manner when there's no thermal mass or forced air cooling. Next, we'll be diving into some details on how to customize your flexible heater for a given application. So a lot of our customers just need a heater, just two wires and a square heater, and that gives them all they need to be successful. But that's not all. Some customers need varying degrees of complexity and components added to provide whatever the heater is trying to do for safety or for other requirements within the system. In terms of options, it's completely up to the customer what you need, where to put it, and how it's going to operate. So we can add temp sense devices like a thermocouple or a thermistor. Those are designed to measure the temperature at a certain place on the heater and then report that information back to some other microcontroller or data acquisition system. If a customer is looking for safety or for something that actually actively turns the heater on and off for a given performance or temperature condition, a thermal fuse or even a thermostat are excellent choices depending on what you're trying to accomplish in terms of operating the heater. A thermal fuse is used more for to prevent against thermal runaway. Many of them, it's a on or off and a one-time use event. The thermal fuse is there for safety. The thermostat is there to control it, and then sometimes can be used in place of an auxiliary microcontroller or other way to control the thermostat. There's also more complex surface-mounted ICs that have the ability to digitally measure temperature and report back to some other device that's monitoring this. Overall, we suggest that our customers define what they're looking for with a given temperature range and potential tolerance band on that temperature. And then we can recommend an off-the-shelf item that we either have readily available or one that we can get. A lot of the US manufacturers that are available on DigiKey and Mouser, many of those items are available where we manufacture in Asia. And if not, there are copious amounts of form, fit, function equivalent temp sense and temp safety control items that we can lean on, given the program requirements for cost, timeline, and performance. So it's not just discrete items like thermistors and thermostats that we can add. It's the actual heat sink or thermal mass themselves. Some of our customers will require a machined aluminum plate. Some of them, it's just a backer plate for rigidity. Others, it's a more complex design based on whatever the requirements for heating and potentially shielding. But no matter what you're trying to attach to this heater, the odds are we can help develop and build whatever this heater goes on to. And as I said before, it's not just temperature sense devices, it's really anything. Any type of connection, any type of interconnect, and any type of thermal management device that you need added, we can develop that solution for you. While most of our customers do need flying leads or just cut ends, a lot of our customers do need us to crimp the terminals on and stuff the terminals inside a connector for whatever the application is. Other customers who have a UL requirements may need us to put on a NEMA 515 type of connector or other power connector that has a UL mark on it, all of which are things that we can support. Lastly, once the heater is designed and built, some customers would like additional layers of customization in the form of a custom overmolded connector. Epec is an industry leader in custom overmolded cables and connections, and adding one of these custom cables directly to a heater is very simple and just involves either soldering or another assembly technique based on what you're trying to accomplish. Next, we'll be talking a bit about some steps that you're going to need to consider if you'd like to move forward with a new project. So before we take the first step, it's important for our customers to understand at a high level what they're trying to accomplish. Has any testing been done? Are there any special materials that are needed? What's the max temperature you're trying to warm this to? Are there any thickness limitations? Is there anything unique about your application that we need to know? Since we can design and build heaters that come already built and shipped with a UL mark, we want to completely understand all of your design requirements before we get too far. If a UL listed heater is needed, we can produce those in just a few weeks. We have the UL listing already. However, not all of our materials, both in thickness and material type, are made with UL recognized materials. Therefore, if a UL mark is required, we need to know that as soon as possible to make sure we steer your design towards something that we can build quickly and within all the parameters that are needed. Lastly, and most importantly, as I said before during this webinar, we strongly suggest to test the heater and plan for at least one design iteration. We can all sit there with calculations that we learned in college to try to predict the wattage we need to raise a certain thermal mass 20 degrees C, and we can get close. However, that isn't an exact science at this point. We strongly suggest building and testing and potentially planning for one design iteration. As we also said, we always make a drawing. Before we build, we will send you a 2D drawing that represents how we're going to build your solution. These drawings will include critical dimensions, features, a bill of materials, and show the total stack up that gives you, the customer, confidence that we're going to build this the way that you expect it to be. These drawings, as I said, are fully dimensioned manufacturing prints that we're going to send to you for your review and approval before we start our build. So before getting started with any kind of project, we suggest that you fill out one of our flexible heater inquiry forms. These forms have a variety of requirements and parameters that we want to hear from you about to make sure we can size your heater properly. Depending on what you're trying to accomplish, our sales team and one of our product managers, we get on the phone with you to walk through the design to make sure we understand what you're trying to accomplish and make sure that these designs meet all of your design requirements. Next, we'll go through a bit of a summary before we wrap up with our Q&A. So Epec provides a free of charge DFM review for all of our heaters. We'll get on a Teams call with you and walk through your design, talk through options, potential lifespan risks, how we would build it, and any other concerns that you may or may not have. We do this free of charge on every one of our products. We also strongly suggest to do some type of benchtop testing early in the process. And we lean on that more than theoretical calculations that we do to size these heaters. The worst thing that we can do is predict a 35-watt heater performance only to find out we actually need 50 watts because we didn't account for some variable. As we touched on before, we have numerous designs with an existing UL approval. That means in just a couple of weeks, we can get you a functioning heater to your exact design requirements with the UL mark on the heater. Some of our customers need that to go to market. Others, it's not as much of a concern. I also want to emphasize we can work with a very minimal amount of information to quote. All we need is the footprint, rough wattage and voltage specs, and any wire specs that you have. And at least from there, get you a budgetary quote to start the process. And then lastly, we have customers who don't know what they want, but they have a heater either that they've already bought from another vendor or maybe have used from another device, and they don't have the design data or experience to develop that. Engaging with our sales team, we can set up a conference call or a review to potentially reverse engineer a heater that you may have that you're trying to duplicate. During that process, we may ask for you to send us a heater. We may destroy it as a part of our analysis, or we may walk you through some measurements that you can do with a handheld multimeter that we would need to go try and reverse engineer that sample. With that said, I'm now going to turn it back over to Ryan to discuss more about some of our products.
Thank you, Stephen. While he reviews the questions that came in, I wanted to briefly mention some of the additional products we offer here at Epec. For more than 70 years, Epec has designed and manufactured custom build-to-print electronics. Our expertise lies in printed circuit boards, custom battery packs, flex and rigid flex PCBs, overmolded and other types of cable assemblies, CNC machining through our sister company, Metalcraft Machining, high reliability user interfaces, flexible heaters, and energy efficient fans and motors. Next slide, please. And now I'll turn it back over to Steve to go through some of the questions that came in.
Thank you, Ryan. First question we have here says, what's the highest wattage heater you can make? So I know the size limitation is what's going to be the issue here, and it's more the watt density. But the reality is, if you're comfortable with a silicone heater with a wire wound heating element, we can make this almost infinitely large. That's not entirely correct, right? But the truth is, as long as our watt density is below 10 or 20 watts per square inch, and that you can provide enough voltage to drive the heater, we can make it as long as you need. The key there is we would need to understand the overall length, the voltage and wattage requirements, and then make sure that we have an opportunity to build some samples first to make sure that our solution meets what you're trying to do. But there really isn't a highest wattage heater, because as much energy as you can dump into it, you hope that you can dissipate that. The next question is, are there limitations for shapes that you can make? The answer is no, because these are completely custom and built from scratch. And what I mean is, we're either die cutting or laser cutting these. So the shape, the perimeter shape of the heater, as long as it's something you can define either through a DXF or some other CAD program, we can produce that. There are some limitations on width. Anything that's going to be thinner than about 1/4 of an inch or so is probably too small. We need to give ourselves room to park 1 or 2 traces and have enough edge distance to seal the film, whether it's polyimide or silicone. So the answer is, there are really no limitations on the shape, as long as it's something that you can define in CAD or in another drawing. The next question here is there such a thing as a double-sided heater? This is a good one. I've actually never thought about this, but the answer is, all heaters are double-sided. It's just a heating element with film on both sides. So in theory, the heater is double-sided. The key is that some customers only put an adhesive on one side and affix the adhesive to a other member on that one side. But there are situations we've seen customers that will take a heater and sandwich it in between 2 plates so that the heat goes in both directions. Next question we have is, what are the standard lead times, and are there additional lead times for non-standard items? So our typical manufacturing time is about 15 business days. That's for material that we have and use and already are building with. If a given application needs an extremely high temperature adhesive or a potentially low outgassing type of polyimide, maybe there's a specialty connector of some sort, our lead time is driven by whatever is on the critical path for that heater. Typically, if there's a long lead or high risk item that we're looking at, we'll work with our customers to flag that, to communicate what's driving our lead time, and to have a discussion to see if there are options that we can consider to give us an equivalent or another type of design that's something we can get sooner, pulling in that lead time. We have time for one more question. It is, are there typical connectors or other typical connectors that are compatible with your power source? So I believe the best way to answer that is most customers just want flying leads, 2 wires that are stripped and tinned. And then our customers do whatever they need to do, whether it's soldering those wires to another board or potentially crimping and terminating them. But there really are no standard connectors. It's any type of power connector that you need that can handle the voltage and current for the given application. Some of these heaters will draw high amounts of current, so we need to make certain that whatever terminal and connector that we are selecting will survive whatever current and voltage requirements the heater may have. So that's all the time we have for this afternoon. I want to thank everybody for your time, and please check out our website or email sales@epectech.com if you have any other questions. Have a great afternoon. Thank you, everyone.